On an average summer night, around 1,500 flights traverse the Atlantic from the United States to Europe. And almost all take this one route, like a highway at rush hour. These planes are separated by only 40 miles in distance and 25 miles laterally. Vertically, they fly as close as 1,000 feet to each other. It takes an immeasurable amount of planning and precision. But why would all of these planes take one route when they have the whole sky, especially when that route is becoming more and more dangerous? To this day, crossing the Atlantic is no easy feat, and that's mostly because of the lack of radar. All air traffic radar communication is through ground-based systems, so when a plane travels across the ocean, radar communication is limited. So planes making the journey follow a structured set of routes called the North Atlantic Organized Track System, or NAT-OTS. These tracks ensure planes are adequately separated and are the reason you've never crashed. Every day, 4 air traffic planning centers map out routes over the Atlantic. The first is the New York station that controls this area. The next is Gander, Newfoundland, and it controls this portion of the Atlantic. Then there's the Santa Maria Oceanic Control that covers this area. North, there's Shanwick, an amalgamation of Prestwick, Scotland, and Shannon, Ireland. Pilots have to report their location every 14 minutes using a computer calculation of their longitude and latitude. Most of the time, it works flawlessly, coordinating a safe passage for the thousands of trips making the nightly journey. But incidents still occur. On February 19th of 2019, a Boeing 787 was caught in a jet streak that pushed it to 801 miles an hour, 200 miles an hour over their normal speed. It broke the sound barrier and came eerily close to other planes. In order to avoid incidents like this, the path must be meticulously coordinated. It's complicated. So why do they take just one route? It's actually because of a Japanese meteorologist in the 1920s. His name was Wasaburo Uishi, and between 1923 and 1925, he completed almost 1,300 observations of fierce high-altitude winds. So when he announced that he had discovered a high-altitude river of air in the sky, he was pretty much ignored outside of Japan. That was a big mistake. That year, Japan launched around 9,000 silk hydrogen balloons carrying bombs into this west-to-east river of air. Around 300 made landfall in the US, and in 1945, tragedy struck in Bly, Oregon, when a Sunday school group stumbled across one of the bombs during an outing. The pastor's wife and 5 students ages 8 to 15 died from the explosion after unknowingly picking up the bomb. That river of air in the sky was now on the US military's radar, and they called it the jet stream.
Jet streams are very fast currents of air that blow generally from west to east all the way around the world in both hemispheres, in the northern hemisphere and the southern hemisphere. And they reach their maximum speeds at altitudes of around 30 to 40,000 feet. And of course, that's a typical cruising altitude for a large commercial plane. There are 2 crucial ingredients for a jet stream to form. One of them is the rotation of the Earth, and the second one is the north-south temperature difference between the very warm tropical regions and the very cold polar regions. You might think that the winds would simply blow in a north-south direction from warm to cold, and indeed that is what they try to do, but no, there's something called the Coriolis force, and that comes from the rotation of the Earth, and it deflects that natural north-south motion into an east-west motion, and that's what gives birth to the jet streams.
Jet streams blow in narrow bands with widths of a few hundred miles and thicknesses of less than 3 miles. They typically average 100 miles per hour in the summer, and they can reach speeds of 200 miles per hour in the winter. U.S. commercial pilots began taking the jet stream into account as early as 1952. It was just practical. When traveling from west to east, it was much more efficient to merge into the 100-mile-per-hour plus tailwinds and be ferried easily across the ocean. It saved fuel and made flights shorter and less turbulent. But But there's one problem with the jet stream air traffic controllers and pilots must account for every day. It's constantly shifting. Jet streams aren't fixed at a certain latitude. They meander from north to south, depending on the time of year and the position of the sun. Every morning at 7 a.m. Eastern Standard Time, NATS has to find it on their satellites and report the course to pilots. They outline the day's flights, requests for preferred routes, and cruising altitudes. This system has worked well since the 50s, when it was put into place, but that isn't to say that it'll keep working well. That's because there's a big problem looming on the horizon.
Several passengers suffered broken bones. Clear air turbulence strikes without warning.
Scientists at the University of Reading published a study in 2019 that revealed significant changes in the jet stream between 1979 and 2017. They observed large increases in vertical shear over the North Atlantic.
Vertical wind shear is simply the fact that the higher up you go in the atmosphere, the windier it gets. But there's this other kind of turbulence that doesn't have any visual signature. You can't see it from the cockpit. Even the radar, the weather radar, can't pick up this clear air turbulence. So it's particularly hazardous, and it's caused by vertical wind shear. So as the wind shear gets stronger because of climate change, we expect a lot more turbulence as well.
The team calls it one of the single largest anthropogenic changes to have occurred since satellite observations began. But what's causing this gigantic change? If you guessed climate change, bingo. Highly fluctuating temperatures due to carbon emissions are to blame. And if we assume that countries do not take drastic action to fix the climate crisis, the amount of severe turbulence is expected to double or triple by 2050 to 2080.
So this is not a hypothetical future change from climate model simulations that people might have some doubts over. This has already happened since I was born, and that's quite sobering for me, in the late 70s.
The consequences won't just be increased turbulence-related injuries like we're seeing right now. Remember when I said that the jet stream was basically a highway with a ton of traffic? With 1,500 planes a day, 40 miles horizontally apart, 25 laterally, and 1,000 vertically? That's fine when the highway's working, but not if that highway turns into the Tacoma Narrows Bridge. Some experts have speculated that the still rising increases in vertical shear will perhaps cause plane crashes in the jet stream if the danger is not taken into account. For the short-term future, this isn't a huge risk. But as we get closer to the conditions that the University of Reading team predicts, it may significantly affect how the oceanic control centers plan flights. Even though the amount of flights have been significantly decreased due to coronavirus travel restrictions, this is an issue that won't be going away in the next 30 to 50 years. It may even affect how many flights there are and their prices. One thing is for sure, flying across the Atlantic is going to become an even more bumpy ride. What do you think of the increased turbulence in the jet stream? Let us know in the comments. Make sure you like this video, click subscribe, and don't forget to ring the bell for post notifications. We'll see you next time.